There's a method here, Newton's method, that's used. What it's used for is to find roots of equations. And best way to put it is to give you an example. Finds roots of equations such as x to the fourth minus 2x cubed minus 2 equals 0. Newton's method finds roots of equations similar to one example such as this. Now, we usually, when we're typically talking about equations and solving them, we don't put it like the roots of equations, but roots of equations, that just means solutions to the equation. Solving equations like this. Now, the problem on it is it doesn't factor. There's not a nice little formula. There's not a nice one. There may be one, but it's complicated. Yeah, that's just a hard equation to solve by hand, I guess one way to put it. And so that's where Newton's method comes in. Now, notice here, we do have one side is 0, and so that is a typical feature to use Newton's method. You need one side to be 0, but it's finding, and that's kind of where the word root comes in. But anyway, it's just basically what we're going to do is solve equations like this. That's what this Newton's method's going to be. It's going to be approximate. Now we get it pretty close, as you'll see through different iterations. Just keep repeating the same process over and over again. But anyway, that's what we're doing. Now, here's what this amounts to. If I graphed this as my function, that's going to give me, whatever it gives me. We'll do that one in just a second, but let's just talk about Newton's method in kind of a generic sense. So if I graph this function, this is not that function, but if I graph the function, call this one, f of x. So if I graphed f of x, let's just do one, not that one. We'll do that one in a second. Actually, I think it is kind of similar to this one, but what I'm drawing here, but. So if I've got f of x equals 0, and I'm trying to find a root or a solution to that equation. That's my goal here. So what I've got here is I've got y equals f of x graphed. Well, I want f of x equals 0. Well, where is f of x equals 0 on this graph? Well, that's y equals 0. And so what I'm talking about, y equals 0, that's an x-intercept. And so one of the roots of the equation that I've got in general graphed here is going to be an x-intercept. So this right here is going to be the root, call it r, that I'm looking for. So one of the solutions to this, I don't have the full graph, so there might be some other ones, but understand what I'm looking for when I graph these is the x-intercepts, okay? That's going to be roots that I'm looking for, okay? So I'm looking for r, which are going to be x-intercepts on the graph, the real solutions. They're x-intercepts here. So that's what I'm looking for. Understand that, first of all. Because I'm wanting equals 0, so it's going to be x-intercepts if it's a real number. So that's what I'm looking for. So what does Newton's method do? Well, Newton's method says, well, let's just take a guess at it. And I'm going to exaggerate it a little bit because I probably wouldn't guess this far off. I'm going to guess real close to that, but because of what I'm going to draw some things in, I'm going to guess a little further away. So let's just say I take a guess out here a guess of x1, okay? That's my guess. Like I said, I probably try to make it a little closer than normally, but because of what I'm going to draw, I'll show you how this works. I need to guess a little further out, but it's usually going to be close in to R. Okay? Well, what Newton's method does is say, well, let's take that x1 up to the graph here. And so that would be f of x1 would be the x value. Newton's method says, well, the next step, the x2 that comes from Newton's method is, it comes from the x-intercept of this tangent line of my first guess. So I take that point up to the curve, and then Newton's method says, well, let's take this tangent line here, and let me make it a little steeper there so I can maybe get an x3 in. And so x2 is going to be the second value that comes out of this Newton's method, and it's the x-intercept of the tangent line. So it's the x-intercept of the tangent line at x1. If you can understand all that. The picture probably is easier to understand. So I take that x1 up, get the tangent line, and so x2 from Newton's method it's a better, closer value to the root, right? Because I've gone from x1 now, x2 is closer. See that? All right, now, working out the fine details here, this line, so this point would be x1 comma y1, which is x1 comma f of x1, right? That's what that point would be. So that tangent line is y, using point slope, y minus y1 equals m times x minus x1. It would be y minus f of x1, right? That's the y1. Equals, now, this is the tangent line, so what's the slope? It's the derivative, right? The derivative gives me the slope of the tangent line. So the m of the tangent line is the slope. So it'd be f prime of x1 times x minus x1. We said this x2 is our y-intercept, our x-intercept of that tangent line. So what would be the x-intercept here? Well, the x-intercept's when y equals 0. And so the x-intercept would be 0, comma, x2 comma 0. That's what I've called it. So that would be y0 and then x is x2. Well, if I solve this for x2 now, because that's really what I'm interested in, here's what I get. Let's divide both sides by, because that goes away, divide both sides by f prime of x1. So that'll get rid of that, and this side will just be x2 minus x1. So x2, if I add the x1 over, x2 equals the x1 minus that. Kind of switch sides here, but you don't have to deal with all this necessarily. You don't have to generate all this each time. This is what I want us to see right there. You just kind of understand what I was doing there. This is what I'm interested in. This x2 value, which is the next best, the next guess, or the next value that comes from Newton's method, x2 is x1 minus the function value at x1 divided by the derivative at x1. Notice x2 is just dependent on the values from x1. It's the x1 value minus the f of x1 value divided by the f prime of x1 value, okay? Well, that's a better guess than x1 was, right? Because it came in closer to the root. That's what I need you to understand, okay? Well, so that's a better one yet. Well, couldn't I do the same thing for x2? Take it up to the function value, to the curve, draw in the tangent line there, and then think about the x-intercept for it. Call it x3. I don't know if you went through enough for you to draw that in, but wouldn't another iteration of that give us a better, because that's closer to the root, right? Because the way the tangent's working. So guess what x3 is? It's a closer value to the root than x2 was. Guess what x3 is? Well, we go through the same thing, but it's going to be pretty much the same here as x2 was. x2 was x1 minus all that. Guess what x3 is? x3 is going to be x2 minus f of x2 divided by f prime of x2. See that? And so that's going to be a better estimate of the root, r, than x2 was. x2 was a better estimate of r than x1 was. See that? And so we could keep going and going here. I could get an x4. x4 then would be the x-intercept of the x3 point, tangent line. This is called Newton's method. Newton's method, here's the formula. The x of n plus 1 better estimate is, you just take the x of n minus the f of x of n divided by the f prime of the x of n. And so x of n is the whatever value, the one you guess, or the one that the formula gives you. The next better one is the x of n plus 1. So it's always this format. Okay? So this is how it works. It just keeps getting those x-intercepts of the tangent lines. Because you kind of have to understand that. There's a couple of problems on the assignment. You kind of have to understand what you're getting as you go along. It just narrows in on, focuses in on those x-intercepts of the tangent line. So if I had, for example, if I had a curve, whatever it does, and so -1, -2, -3, +1, +2, +3. Okay. And so if I guess, here, this x1 equals -1.5, apply the Newton's method to it, it's going to give me, it looks like it's a little over from -1.5, but if I guess -1.5, then x of 2 is going to be a little better, x of 3 is a little better, so Newton's method will give me that root. And then x over here will be x of +1.5. I mean, make them both about that, but that's, if I guess x1 is that, then it's going to give me that root. So you see, it narrows in on whichever one is closest, usually the one that's closest. Now if I guess The only, I mean, I could guess any whole number, integer, I could guess x1 is 2, and it would give me that value. What you don't want to do is guess, if I do, because it's based on the tangent line, if I take a guess, let's say that's out here at 5, I can pick any x value I want. I just don't want to pick 5 because if I do a tangent there, it's going to run parallel to the x-axis. That's not going to give me an x-intercept. So if I guess x1 is 5, you're not going to get a root there from Newton's method. And so that's kind of what you have to understand on the questions, I think, on the homework. What gives you a root and what doesn't. So anyway, it's based on the tangent line. The tangent line goes horizontal, you're not going to get an x-intercept, so Newton's method won't work. Okay, so let's actually do a couple of these here. Let's do that one I just had, all right? So, well, tell you what, let's do this one. All right. So, find the third approximation for the root in 1, 2. This is kind of the wording they have in the book, so that's why I'm wording it like this. Find the third approximation for the root in 1, 2. Interval 1, 2 for the equation x cubed minus 3x plus 1 equals 0. Okay, find the third approximation for this root. Something else. Starting with x1 equals 2. All right, so I've got the starting place here, x1 equals 2. Now, x2 then would be the second approximation. I want the third approximation, so I want to take this to x3. So let's do x2, and then we'll do x3. So what's x2? Well, x2 is, from the formula, x2 would be x1 minus f of x1 divided by f prime of x1. So we're going to do this one by hand, then I'm going to show you a nice thing, how we can do it on the calculator there. All right, so x1 is 2, so it'll be 2 minus f of 2 divided by f prime of 2. What is f here? This is f of x right here, isn't it? X cubed minus 3x plus 1. So f of 2, I'm just going to plug in 2 to this function here. So it'll be 2 cubed minus 3 times 2 plus 1. Let's write it here. All right, so it's right here. So 2 cubed minus 3 times 2 plus 1. Put it right there. I want to divide that by f prime. So what's f prime? Well, f prime is just the derivative here, so it'd be 3x squared minus 3. So f prime of 2 would be 3 times 2 squared minus 3. And we're going to do these by hand and then show you a better, quicker way of doing it. All right, so what have we got? 2 minus, that would be 8 minus 6 plus 1. Is that 3? 8 minus 6 plus 1 is 3. Divide that by, this would be 3 times 4, so it'd be 12 minus, is that 3 over 9? 2 minus a third. Should be 1.6 repeat. Because most of these that we get will be decimal forms. All right. And, well, since we're doing it by hand, it may be better to write it as a fraction here. 2 minus a third, so it's 5/3. Okay. Well, it wanted the third, that's the second approximation. The third approximation, x3 then, x3 is x2 minus f of x2 divided by f prime of x2. Well, x2, like I said, is 5/3, so it'd be 5/3 minus f of 5/3 divided by f prime of 5/3. Which that'll be 5/3 minus f of 5/3, so that would be 5/3 cubed minus 3 times 5/3 plus 1. Divided by f prime of 5/3, so that would be 3 times 5/3 squared minus 3. Okay, so put that in the calculator. 5/3 minus, and I would just, if we're doing this by hand, just put all that in parentheses. Probably the best way to do it if you want to do it all at once. Let's see, parentheses would be 5/3 cubed minus 3 times 5/3 plus 1 divided by parentheses 3 times 5/3 squared. See, this is cumbersome after the first couple of these. This is the second one, the third one. I get 1.58461111, which does have a decimal, but said we want, a fraction, but all right. So that's what it is. Let me show you how to really get this going. Here's what we can do. With these graphing calculators, you got some nice features on those, and some of them have a lot more, but here's what we can do. All right, let's do this same problem. But let's use the all right. So our first guess was x1 is 2. And then the second guess is based on that. But here's the way we can set this up. Put in 2 and hit enter. Oh, this is with the TIs, okay? So get x1 is 2, hit 2 and hit enter. Well, what that sets up then is 2 is the answer for when I hit 2 enter. That means 2 equals the answer. 2 is A and S, is what the TIs call it. For x2, I'm not going to put in the 2. Here's what I'm going to do. I'm going to put, instead of 2, I'm going to put A and S. There's a button on the calculator that takes the previous answer. There's an A and S button, if you will. On the TI-84s, it's right above the negative sign at the bottom, that blue A and S. I'm going to use that button in the place of 2 here. So instead of 2 here, I'm going to put in A and S. All right, so wherever I see a 2 in this, I'm just going to put A and S. So it'll be A and S, I'll write it up here, A and S, I'm going to hit that button, minus, parentheses, A and S cubed, minus 3 times A and S, plus 1, divided by 3 times A and S, parentheses, 3 times A and S squared, minus 3. If I put that in there like that, that'll be very, very helpful. So A and S minus the function value at A and S, so it'd be A and S cubed minus 3 times A and S plus 1. And divide that by 3 A and S squared minus 3. Hit enter. Should get the 1.66 repeat, okay, that we got here. Well, the beauty of this then is if I hit A and S again, not A and S, if I hit enter again, it's going to repeat the previous step on the calculator. If I hit enter, after I get all that done, if I hit enter again, guess what I get? I get x3. Just by hitting enter again, because it repeats the previous entry. If I do that, and the previous entry was this, but why did it make it different? Because the A and S is different, you see. It picks this up as A and S. Now this is A and S. And so when I hit enter again, it just does that whole thing again, which is exactly what I needed to do, is I need to take this and plug it into that. Just hitting enter does it, you see. So it's really, really nice. Now, what this means is, once I get that all done, this is cumbersome doing by hand, but once I get it entered like that, just keep hitting enter. So x4, hit enter again, you got 1.532390162. You see? It gives me the next better estimate. Hit enter again, x5 then is 1.532088989. I'm writing them all because notice if I keep doing this, x6 is 1.532088886, and then x7 notice is 1.532088886. The same exact thing. Now, that's not an exact value, there's more decimals after that, but I've got this root to 1, 2, 3, 4, 5, 6, 7, 8, 9 places. Because the rest of them, the rest of the changes in the decimals are way out here. So this is correct to 7, what did I say? 9 places. See. Okay? All right. Let me show you one more. So this would be the root correct to 9 places. We've got it pretty well lined out there. All right? Okay, so let me do another one here, and we'll go kind of step by step of it, because this is definitely the way you probably want to go. All right. Find a root of cosine of x equals x squared minus 2x to 6 decimal places. Now there's a couple of points on this one. Point number one is, for this Newton's method to work, you remember what we needed the equation equal to? One side to be? We need one side to be 0. So if one side is not 0, you need to make one side to be 0. Okay? So let's move these terms over either way. So cosine of x minus x squared plus 2x equals 0. Then that establishes our f of x. This will be f of x. Just right here. Okay? So I want to find a root of that. Well, it didn't give me a starting place. So graph this function here. Cosine of x minus x squared plus 2x Okay, well, it looks like there's two roots. Two real roots, right? That's the x-intercepts. Because this is the graph of that, right? So there's two roots I can find here. They'll probably want you to find both, but we'll just find one. You just do one at a time, of course. So let's just find that this first one, the one on the far right here, looks like it's at 2. About 2. So that's going to be my x1. That's my first guess. x1 equals 2. Similar to the previous one. Well, with Newton's method, then x2, how do we get x2? Well, x2 is x1 minus f of x1 divided by f prime of x1. But for the calculator here, what I'm going to do is instead of x1, I'm going to say that's a and s minus f of a and s. That's the way the TIs do it. F prime of a and s. So in this case, what is that going to be? Well, a and s, what's f of a and s? Well, it's just cosine of a and s. Minus a and s squared plus 2 times a and s. That's what it's going to look like. What's f prime of a and s? Well, f prime then is negative sine x minus 2x plus 2. So the derivative evaluated a and s would be negative, put parentheses around it, negative sine of a and s. That's how you enter it. Minus 2 times a and s plus 2. If you enter it like that, then it's just hitting the enter key over and over again. Now, again, the first thing you need to do, though, is hit 2 and then enter. Back on the calculation screen, 2, hit enter. That sets in 2 as the answer. Now, let's do a and s minus parentheses cosine of a and s minus a and s squared plus 2a and s, goes off the parentheses, divide by, minus sine of a and s, minus 2a and s, plus 2. And then just hit it. It's 1.856959679. This is, I'd like for you to show me each, you don't have to show me all this. Show me each value that you get. But now it's just then just hitting enter. So the x3 would be 1.850729975. x4 then would be 1.850717442. x5 is 1.85071. Oh, it's the same thing. So there you go. There's your root. Now let me show you this one more thing, because now that's one of the roots. Okay, that's one of them. There's a second one, and there may be 2, there may be 3. The second root is over here. It's closer. Let me go back to the graph. It's closer, like negative a half. So how would I get it? Well, x1 would be negative a half, negative 0.5. To get x2, I need to do this all over again. But let me show you here. If you're using the same function over again, hit your negative 0.5, hit enter. Okay. Now I want to come back to this. So if you go to the entry, you don't have to do it this way. I mean, you can enter it all again. But if you go to the entry button, second, and then enter, get you the entry. Well, that's, the first one comes up as the negative 0.5, but if you hit second entry again, it'll bring this right back up. And so it kind of resets it. So, yeah. If you want this again, go second entry twice. Once you put in the negative 0.5, hit second entry twice. Second enter. The second, and then enter. And do that twice. It'll come back to this. I'm just showing you a way to get to it. I mean, you can put it all in again if you want to, right there, but that's a quick way to do it. And so this gets us negative 0.392, 965, and then you just keep hitting enter, and you can find that second one. Okay? All right. Well,